Every calculus class teaches the same trick. Bring the exponent down in front, then knock one off it. It works. The derivative of x squared is 2x, and nobody ever tells you why. For 3 lessons, we differentiated exactly one curve, x squared, and every single time the answer came back 2x. We never once said where that 2 came from. Today we do. By the end, that 2 will not be a rule you memorized. It will be a length you can point at. And the picture is the oldest one in mathematics. X squared is a square. A square with side x, its area is x times x, which is x squared. So a curve climbing like x squared is really a square growing, which makes the derivative a very physical question. If the side gets a little longer, how much new area appears? Push the side outward by a tiny amount. Last lesson we called that tiny step delta x. From here I will write it dx, which means the same thing, a small change in x. Push it out and the square grows in 2 directions at once, to the right and upward. Along the right edge a thin slab appears. It is x tall and dx wide, so its area is x times dx. Along the top edge an identical slab appears, another x times dx. 2 slabs, each of area x times dx. Together 2x times dx. There it is. The 2 and 2x is not decoration. It is the number of sides that moved. That is the honest version of it. A square has 4 sides, but only 2 of them push outward, 1 for each direction it can grow. So 2x is the perimeter of the growing square, meaning the total length of the border where new area lands. Now look at the far corner. The 2 slabs do not quite meet. There is a tiny square left over, dx by dx, with area dx squared. So the new area is 2x times dx plus dx squared. Every piece accounted for, nothing swept under the rug. The derivative is not the new area. It is the rate, so we divide the new area by the size of the step. Divide each piece by dx. 2x times dx over dx is 2x and dx squared over dx is dx. So the rate reads 2x plus dx. Now shrink the step and watch which piece dies. Take x equals 3. With a step of 0.1, the 2 slabs add 0.6 and the corner adds 1/100th. The corner is under 2% of all the new area. Shrink the step to 0.01. The slabs give 6/100ths. The corner gives 1/10,000th. Its share has fallen to about 1/6 of 1%, and it keeps falling. Here is why, and it is worth saying properly. The slabs carry 1 factor of dx. The corner carries 2. So after you divide by dx, the slabs keep their full size, and the corner is the only piece still holding a dx. That leftover is exactly what Lesson 1 built a machine for. We never set it to 0. We watch where the reading is heading as the step shrinks. It heads for 2x, and now that answer has a picture behind it. 2 sides of a square are moving. If x squared is a square, then x cubed is a cube. Side x and volume x times x. Ask the very same physical question. Push every side out by dx, and how much new volume appears. This time the new material lands on faces, not edges. There are 3 of them, 1 on the right, 1 on top, 1 on the front. A cube has 6 faces, but only 3 can move outward, 1 for each direction. Each face slab is a square of side x, dx thick, so each one holds x squared times dx. 3 faces, each x squared times dx. That is 3x squared times dx. And there is the 3, dropping down in front of the x squared, for exactly the reason the 2 did. The leftovers are still there. 3 thin bars along the edges, and 1 tiny cube at the far corner. But every one of those carries at least 2 factors of dx, so they all die the way the flat corner died. Check it with real numbers. A cube of side 2, pushed out by 1/10, gains 1.261 in volume. The 3 face slabs account for 1.2 of that. The bars in the corner are the small remainder, and they shrink far faster than the step does. So the derivative of x cubed is 3x squared. 2 cases in, and the pattern is already talking. X squared gives 2x, x cubed gives 3x squared. And the reason is the same sentence both times. The number out front is how many faces are moving, and each moving face is the shape one dimension down. So try x to the fourth. There is no fourth dimension to draw on a page, but we do not have to draw it. We only have to count. X to the fourth is a cube in 4 directions. Push all 4 outward, and 4 faces move. Each of those faces is the ordinary 3-dimensional cube, x cubed. So the new amount is 4x cubed times dx, and the derivative of x to the fourth is 4x cubed. Now say it for any whole number n. X to the n is a cube in n directions. Push all n of them outward, and n faces move, each one of size x to the power n minus 1. So the derivative of x to the n is n times x to the power n minus 1. Bring the exponent down in front, knock one off it. Same trick you were taught, except now you know it is counting faces. If you would rather see it in algebra, multiply out x plus dx, n times over. One term has no dx at all. Exactly n terms carry a single dx. Every other term carries 2 or more, so every other term dies. Let us run it a few times, because a rule you cannot use is not a rule yet. X to the fifth, bring down the 5, knock one off, 5x to the fourth. Now a quiet one. X on its own is x to the first power. The rule gives 1 times x to the 0, which is just 1. And the picture agrees. A segment of length x pushed out by dx gains exactly dx, 1 new piece per step forever. A constant is quieter still. A number like 7 never grows at all, so its rate is 0. 2 lessons back we ground out the derivative of x squared by hand, with limits, and it took a whole video. The rule gives the same 2x in 1 second. In last lesson, we added up 2x and got x squared back. That loop closes from both sides now. One exam trap said out loud, the rule is for x raised to a power with a plain fixed number upstairs. It is not for 2 raised to the x, and it is not yet for a curve tucked inside another curve. Those are later lessons, and they get their own pictures. The exponent was never a trick. It was a count of how many ways a shape can grow.